Okay. So we're going to try to figure out a general A sub n for this sequence. All right, so the very first thing you do when looking at this problem is you need to look at the characteristic equation. Now, the characteristic equation, we're going to shift these over to the other side. And so that'd be t squared minus 2t minus 3, which would equal 0. Okay. Now, once again, why do we look at second order differential equations, recurrence relations, anything like that? It's because we have the quadratic formula to just go ahead and give us the answer. But on a lot of these problems, you can just factor it. So if I was going to factor this, it would factor into t minus 3 times t plus 1, which equals 0. Okay, that's just our normal factoring. Okay. So t would equal 3 or t would equal negative 1. That's just the first step of the problem, is finding the roots of the characteristic equation. Okay. Now, from our definition that we were looking at just a second ago, we said, okay, now, if we have the characteristic equation, and we solve for the two distinct real roots, and in this case we do have two real distinct roots, which is going to be 3 and negative 1. So what is the r and the s that is appearing in this equation right here? It's 3 and negative 1. Those are the distinct roots of the characteristic equation. So the very first thing is to formulate the problem into its characteristic equation, and then solve that characteristic equation, find the roots of it, and if you got 2 of them, you're going to go with this formula. We'll have a discussion here in a minute. What happens if you have 1 real root? Or you can even end up in the concept of complex roots. Okay? So normally this is divided into 3 cases, where you have the concept of 2 distinct roots coming from the characteristic equation, 1 real root coming from the characteristic equation, or you can end up with complex roots coming from the characteristic equation, and this applies even into differential equations. So, in general, we're following this formula because we have 2 distinct real roots, 3 and negative 1. Okay? So this tells me that the general sequence of this recursive relationship A sub n is going to equal c multiplied by 3 to the n plus dd multiplied by negative 1 to the n. Okay, great. All right. So where we at the problem at this point is that we found the general solution to this, okay? But to nail down the exact unique solution to this, we have to use our initial conditions, okay? So now that we've gotten to this point, I'm going to go ahead and isolate this. Okay. So just from the characteristic equation, we got to that point of the problem. Okay. Now, we are going to use A naught, which equals 1, and A1, which equals 2. So, from the characteristic equation, we got to a general solution. Now that we have a general solution to this, what are we going to use? We're going to use our initial conditions. Now these initial conditions will help us to isolate, to figure out what C and what D are. Okay? So, let's start a new page. Let's start off with A naught, which equals 1. Okay. So, A naught would equal C times 3 to the 0 power plus D multiplied by -1 raised to the 0 power. Okay? And I said just a second ago that A naught was 1. So 1 would equal C plus D. Okay. And now we're going to use our next condition. What we had was A1 equals 2. Okay. So A1 would equal C times 3 to the first power plus D multiplied by -1 raised to the first power. So we're just swapping out the powers of these. Okay. But on the previous page I said A1 equals 2. I'm going to make that look just a little bit different, but the -1 to the first power is just negative, so we'll just leave it like that. Okay, now with a second order recurrence relation with constant coefficients, why are we using 2 initial conditions? Okay, the reason that we are using 2 initial conditions to try to figure out the constants that create our exact solution is that, what does this create? It creates a 2x2 system, okay? So instead of, I'm going to rewrite this as just, let's say, all right, we figured out what A naught, the equations associated with A naught and A1 are. So just isolate that right there. And so if I look at those equations, 1 equals C plus D, and 2 is going to equal, you know what, I'm going to move that 3 to the other side just because it's easier on my eyes. 3C. minus D. Okay. Now, within a system of equations like this is really more of a linear algebra thing. You all should have learned systems of equations at some point. We could form this into a matrix. We could use substitution. You can do a lot of things with it. But the easiest way to do this problem is through a process of elimination. That's just what happens if I just add these 2 equations together. I'm going to eliminate D completely from the problem. Okay. So if I took these 2 equations and added them together, I'm going to get 3 is going to equal 4C. So, you can say C would equal 3 divided by 4. Great, I got one of them, figured out what C was. And I don't want to waste a lot more paper, so I'm going to do this next part just right over here. So, now that I figured out that C is going to equal 3 divided by 4, that means that 1 would equal 3 divided by 4 plus D, and then you just subtract 3 over 4 from both sides of the problem. And we're going to get that D is going to equal 1 minus 3/4, which is 1 divided by 4. We got to So now we've used the initial conditions, we have used A0 and A1 to turn this into a 2x2 system, which in this case, what did we do? We used just basic elimination to figure out what C and D are. And what this does is this gives us a general solution to the problem. So instead of talking about the recurrence relation, what do we end up with? We end up with a single sequence that will tell us what A sub n is for any n, okay? So, out of all of this, what did we get to? We got that the general sequence for this recurrence relationship is going to equal 3 divided by 4, and then multiplied by 3 to the nth power, and then plus 1 divided by 4, and then multiplied by -1 to the nth power. So, instead of viewing this as a recurrence relationship, we can actually turn this into a single sequence and get the general solution of, so that we wouldn't have to think about, if you were viewing this as a recurrence relationship and you wanted to figure out what A sub n was, you would have to start at A1 and A0, and then you would have to take steps forward repeatedly, I mean going onwards until you, let's say you were looking for A1 billion, okay? So the billionth step of this problem. If you tried to do this through a recurrence relationship, you would literally have to go A1, well, I mean, A0 and A1 are given, and then you'd have to go to A2, then A3, then A4, then A5, A6, A7, A8, all the way off to a billion, okay? But if you use this concept of that this is a second order homogeneous recurrence relation, you turn it into a sequence itself, and then what can you do? If you want to figure out what A sub billion is, plug a billion into this, okay? So you don't take the 999,999 steps to get there, okay? So that's the concept of this relationship.